On this slide, we want to talk about important concept of quasi-compactness, and in particular, what are open subsets of, say, a affine algebraic set. So first, you start with fixing a set X as an affine algebraic set, and this set X is covered by some open sets. So we still have to show you what open sets are, but say there's a union of open sets which covers X, and this union could be infinite. Now the idea is that we say that X is quasi-compact, that there are only a finite number of sets, finite number of U alphas required to cover X completely. So that is what quasi-compact means. So notice first I'm drawing an affine algebraic set X in terms of a parabola. So what is U alpha? So you take finite number of points out of X. So U alpha is precisely like X, but you take finite number of points out. So I've taken 4 points out here. Now how did I take these points out? We will come to it like these. So X minus U alpha consists of these 4 points. So how did I take these 4 points out? Basically there is a polynomial which cuts X, so say some polynomial f which is cutting X, and it cuts X at 4 points, and those are the 4 points precisely which I have taken out of X to get U alpha. And X minus U alpha is a closed set, as you can see, because U alpha is open. So now notice if I take X minus its cover, you get a null set. Now you apply De Morgan's law, you get X minus U alpha like this. Yeah, so you have applied De Morgan's law. Now why am I writing like this? So now you see on the left hand side there is a null set, and therefore we will end up applying the null Stellensatz. And this point you should keep in mind. You see an empty set, think of applying null Stellensatz. So now X minus U alpha is closed set of X, as you can see pictorially on the left side, or you can see U alpha is open. So I alpha, you define I alpha as all those regular functions, the ideal of all those regular functions on X that vanish on this set X minus U alpha. So X minus U alpha, as you can see, are 4 green points which I have drawn indicatively. So all those polynomials which vanish on it. Now what you do is you define a new ideal J, which is sum of all these ideals, yeah, for each alpha. So I alpha belongs to J. Now the vanishing set we apply, inclusion is reversed. Now this is equal to, just I'm copying the definition down, X minus U alpha is closed, so we get X minus U alpha here. Now each X minus U alpha contains vanishing set of J, so their intersection also contains the vanishing set of J. In particular, this intersection is null set, as we have written in the first line. Yeah, null set is equal to intersection alpha X minus U alpha, which implies the vanishing set of J is the null set, and therefore now you apply the null Stellensatz. If vanishing set of an ideal is null set, that means that ideal generates the entire ring. So the entire ring OX, which is associated with the affine algebraic set X, is generated by the ideal J, or J generates 1. Now if it generates 1, that means J is element of this set. Yeah, here we are saying that alpha could be anything, yeah, but in rings you have to give precise meaning. So because we are working within rings, this will become finite. So there is a finite sum J equals to 1 to R ij, and all these ij's are drawn from I alphas. So this finite part comes from working in the rings. Yeah, rings only allow finite sums, they do not allow infinite sums. So 1 is generated by finite number, precisely because when we work in rings we have to give this number as a finite number, and that is what I am going to copy it down here. And now we are almost done. We just need to retrace our steps. Okay, so the ideal J which generates 1, obviously J generates the entire ring, or J generates 1, and we are just choosing those ideals which precisely generate 1. So that is the end of the story. Now we are just writing it down. The vanishing set of J is the null set, which you are writing like this, but you know the summation sign becomes the intersection for each J. Now we are almost done. Yeah, so what is this intersection? So this intersection is nothing but right here. It is those ij's are nothing but ideal of x minus u alpha. So vi becomes x minus u alpha because x minus u alpha is closed set. We have used that before. Vi of x minus u alpha is x minus u alpha. So this will be x minus uj, and now you apply the De Morgan law again. You get x minus, yeah, so this is the finite cover. Now you see x minus this finite cover is the null set, and you are done. So you, from all the alphas, you were able to choose R elements which precisely cover X. So X is quasi-compact, and that is the end of the story. So the basic argument is that in the ring, when you have one is generated by a sum of finite number of elements. You cannot have one generated by infinitely many elements of the ring, and that is the fundamental thing. And from there and the null set, everything else follows.